According to a study by the International Organization for Standardization, 7 out of 10 professionals fail to accurately distinguish between quality assurance and quality control. This semantic ambiguity carries a heavy operational cost. Mislabeling these functions leads to misallocated resources and reactive testing loops that catch errors far too late in the production cycle. To correct this, we have to examine the overarching architecture. A quality management system provides the structural foundation that houses both disciplines. When that management pipeline breaks down, the physical consequences are highly visible. An automated robotic arm dropping a heavy payload on a moving manufacturing line is rarely just a spontaneous glitch. When teams cannot distinguish between the process used to build a machine and the test used to verify it, vital responsibilities overlap and critical checkpoints vanish. The dropped payload is simply the tangible result of this invisible mismanagement. Quality assurance is a proactive, process-oriented function. Its explicit design and purpose is defect prevention. Quality control is a reactive, product-oriented function. Its explicit design is strict defect detection. These are two parallel, distinctly separate operational timelines. When an organization treats these distinct functions as interchangeable synonyms, workflows tangle. The structural integrity of the entire system breaks down. True quality requires decoupling the process from the product, establishing the rules separately, and then integrating them logically. A common misconception assumes that QA and QC share the same daily functional goals. They do not. A QA workflow relies on specialized documentation, utilizing tools like standard operating procedures and quality manuals. QA maps and governs the workflow rules entirely before any physical production begins. Conversely, the QC workflow utilizes a different toolset: statistical sampling, automated testing, and physical inspections. QC acts exclusively on the outputs. It evaluates the physical result, remaining completely blind to the rules that created it. QA engineers the rules of the system, while QC acts as the auditor, verifying the execution of those rules. Another widespread myth positions QC merely as a final filter applied at the very end of a project. Using quality evaluation purely as a post-production net is mathematically inefficient. We see this clearly in the software development lifecycle, where continuous integration serves as the standard. This chart overlays a project timeline with data from the National Institute of Standards and Technology. The cost of a single defect multiplies by 10 moving from planning into final testing. Integrating early QC checks prevents this financial compounding. By pushing testing backward, organizations avoid the exponential multiplier. Delaying quality evaluation until the end of a project guarantees maximum financial and operational loss. Even with perfect process mapping, assuming a QA system guarantees a zero defect output is a statistical impossibility. Industry data indicates that up to 30% of products may still exhibit variance despite robust planning frameworks. This control chart visualizes why that inevitable variance requires an empirical safety net. Here, a specific data point is breaching the acceptable threshold limits. When a breach occurs, organizations use the Corrective and Preventive Action Framework, or CAPA, to link detection back to prevention. The sequence is exact. QC detects the anomaly, which triggers a CAPA, forcing QA to update the original process limits. Through the CAPA framework, QC functions as a vital sensory organ, feeding real-world failure data back into the system to force evolution.
Strict QA and QC frameworks are often incorrectly viewed as necessary only for heavy physical manufacturing. In the pharmaceutical sector, regulatory affairs relies entirely on these disciplines to function. Securing global drug approvals requires rigid adherence to good manufacturing practice, or GMP. In these regulatory environments, data integrity is an absolute legal requirement. Every batch record, lab result, and submission document must be pristine. Modern pharmaceutical and software regulatory environments must process massive volumes of data at high speeds to maintain this compliance. Standards like ISO 9001 are utilized globally to unify and standardize these documentation practices across completely different sectors. In regulated industries, the standard of proof is identical. Proving the process works is legally the same as proving the product works. QA and QC cannot sustain long-term operational success in isolation. Total quality management is a holistic philosophy that demands both process oversight and product evaluation working in tandem. This continuous cyclic diagram visualizes the unified quality engine in its proper sequence: process design, execution, output testing, data analysis, and process refinement. With each completed cycle, internal friction drops and system variance decreases. QA engineers a reliable theoretical system, but QC empirically proves that system exists in reality. Organizations that implement this dual framework see hard return on investment metrics. When proactive process management pairs with rigorous output verification, organizations report up to a 50% reduction in overall defects. This precision leads directly to a 30% increase in customer satisfaction and a 20% increase in overall project success rates. When proactive systems and reactive systems are perfectly aligned together, the entire organization gains massive operational momentum moving forward. This data-driven cycle of establishing baselines and refining the system ensures that quality becomes a continuous operational state rather than a final hurdle to clear.